Hello students, ethers, their structure, preparation methods, chemical reactions. Dear students, what is ether? Ether is a compound which is having oxygen bond in between alkyl or aryl groups. For example, if I take dimethyl ether or methoxymethane, this is a symmetrical ether which is having sp3 hybridization of this oxygen, and the shape of this molecule is tetrahedral, and the bond angle is little higher than the usual tetrahedral. Usual tetrahedral bond angle is 109.28 minutes. However, because of this repulsion of these two bulky groups, the usual bond length is higher than the usual bond length of sp3 hybridization, and the bond length between carbon and oxygen is as usual same as in alcohols, where it is 142 picometers. In ethers it is 141 picometers. Let us see what are the different types of ethers. Symmetric ethers are simple ethers, mixed or unsymmetrical ethers. That means the ether is going to have different groups. For example, symmetric ethers: methoxy, methane, C2H5O, C2H5, ethoxy, ethane. This is mixed ether. For example, this is dimethyl ether. The common name is dimethyl ether. This is diethyl ether, methyl isopropyl ether. Whereas the IUPAC names are like this: methoxy. Write the name as methoxy, methane. There should be no gap between methoxy, methane. Then ethoxy, ethane. Whereas this is a mixed ether where one side alkyl group is methyl and the other side alkyl group is isopropyl group. This nomenclature follows like this: 2, 1, 2, 3, 2 methoxy propane. Let us take some aromatic compounds. This is one of the mixed ether where one side is aryl group, other side is methyl group or alkyl group. Common name is anisole, and the IUPAC name is methoxybenzene. When it comes to C2H5, the common name is phenol. It is ethoxybenzene. Let us take one cyclohexane ring. The nomenclature of this, if I ask you to write C2H5, then where the numbering starts? Dear students, the gem dimethyl group gets the priority over this oxygen or ethoxy group. So the IUPAC name follows like this: 2-ethoxy, 1,1-dimethyl cyclohexane. So what are the common preparatory methods of these ethers? Let us see. Yes students, preparation of ethers. So usually there are two methods. One is dehydration of alcohols, and the second one is Williamson synthesis, which is very important synthetic method for the synthesis of ethers. Williamson's ether synthesis. Let us see one by one. The first method, let us take ethanol, for example CH3, CH2, and this is alcohol. When I treat it with sulfuric acid, say usually concentrated sulfuric acid or H3PO4 you can use. So if I use sulfuric acid, it is temperature dependent. At 170 degrees centigrade, at high temperatures, it undergoes elimination reaction to give alkene, so which is not required to us, alkene, because of elimination reaction. Then how to make this? At lower temperatures, yes, you can get at about 140 degrees centigrade, you will get, let us take 2 moles of this CH3, CH2O, CH2, CH3 plus this water molecule. Dear students, this molecule is diethyl ether, or I can name it as ethoxyethane. The usual way of writing this diethyl ether is like this: diethyl ether, or I can write ETOET, or I can write the same compound C2H5O, C2H5. These are all the usual methods of representing this diethyl ether, which is a common solvent used in organic synthesis. Yes students, so what is the mechanism? How it is going to form diethyl ether. So since we are using H2SO4, it is giving H plus ions, and we know that the oxygen is going to have lone pair of electrons. So this alcohol is going to take up proton to give CH3. Oh, hydrogen already is there. New hydrogen has come here, and now what is the charge? Oxonium ion. This oxonium ion under SN2 reaction conditions, bimolecular nucleophilic substitution takes place, where another molecule of alcohol enters from backside and it is going out as water molecule. Minus, this is water, and what is left over? Here it is CH3, CH2O, hydrogen is present here, plus and CH2, CH3. Now it is very simple. It loses hydrogen minus H plus ion. Yes. So here whatever is added here, it is coming out. So CH3, CH2O and CH2, CH3. So this is how I can prepare diethyl ether. Demerits of this method. What are the demerits? It is SN2 reaction. If I take here secondary alcohol or tertiary alcohol, it is not going to give ethers. It is going to give elimination products. So secondary or tertiary alcohols are not useful in this method. For example, if I take here tertiary butanol, so at this stage it easily loses water, and the formed carbocation easily takes up this proton and gives elimination of this. It is going to give, this is the unexpected or unwanted product. Yes, 2-methyl propene we are going to get. So this is one demerit. And even if I want to make diethyl ether with sulfuric acid, control over temperature is not there. So if I just increase the temperature, we are going to get this, but it is not required to us. We are specifically required this diethyl ether. So this is another drawback. And the third drawback is mixed ethers. For example, if I want to prepare CH3, CH2OH plus CH3OH, that means CH3 methoxyethane. If I want to make methoxyethane, I have to take the mixture of these two alcohols. When I treat it with sulfuric acid, which alcohol is going to give this ether? There is a chance of giving this diethyl ether 1, and chance of giving this, and there is a chance of giving this dimethyl ether also. So if I want to make mixed ethers, I am going to end 1. So 3 products I am going to get mixture of these 3 products. So what is a versatile method for the preparation of ethers is Williamson's synthesis. Let us see. Take alcohol, make the salt of alcohol just by treating sodium, for example, RONA, add alkyl halide to give sodium bromide. So this is the ether we are going to get. This is tertiary butanol plus methyl bromide. In presence of sodium, I am going to get OCH3. So what is the mechanism involved here? First, make this alcohol into sodium salt to give sodium tertiary butoxide. It is a mild base. So since it is H plus, so it makes salt with sodium, and here it is going to have partial negative and this is partial positive charge. Now when I add methyl bromide, what is going to happen? This is negatively charged. It is going to out and this comes in to give this ether which is required or which we are in expected compound O, and this is methyl, and the leftover is sodium and bromide. And since it is very versatile and simple method, then what are the important things to be kept in mind while doing this type of etherification? So this method is known as etherification of alcohols. In this case, the important thing is that you have to choose the tertiary or secondary alcohols as alcohol part, whereas this side it should be primary halide, primary alkyl halide. Otherwise, what is going to happen if I take this side, for example, bromide plus methanol, you may say like this also. So am I going to get this? No. In presence of sodium, sodium methoxide is going to form first. So what is going to happen? Sodium methoxide. This sodium methoxide is base also. It is in alcohol solution, that is methanol is an alcohol solution and it is a base, strong base. Alkyl halides in presence of alcoholic base undergoes elimination reaction. Why? It simply goes out this bromine and it is going to form positive charge, this CH3, this CH3 and this CH3. Now this is stable one. Instead of allowing this molecule, since it is tertiary compound, it is not going to allow this molecule. It simply loses one hydrogen, minus one hydrogen. It gives double bond CH2 and CH3 and CH3. Yes, and the leftover is methanol will be as it is. So choose the alcohol part as tertiary or secondary if you want to make these type of alcohols. Otherwise, if you want to make symmetric alcohols, no question, you can take any of these and do. So here if I take phenol and take methyl iodide or bromide and the modified series of Williamson series, I can use potassium carbonate and acetone as a solvent. I am going to get methoxybenzene. This is one of the usual methods for the preparation of anisole plus carbon dioxide. Or I can use methyl bromide or methyl chloride. So here usual method I can use is sodium. Let me use the same sodium. Here sodium bromide, it is going out. I can use methyl iodide, methyl bromide or methyl chloride. So however the reactivity order is like this. Methyl iodide going to react very fast, then methyl bromide, then methyl chloride. Yes, and moreover methyl iodide comes as liquid at room temperature. So usually we use methyl iodide. What is mechanism here? It is going to form this here and it goes out. So this is how Williamson synthesis is very versatile and important method for the preparation of these ethers. Then question comes, if I take this side iodide and use methanol and use same sodium, am I going to get this? So this is methyl part, this is methyl part, this is oxygen, and here phenyl iodide. Is it possible to make this? No, because the Electrophilic substitution on this carbon is not allowed or is not possible. Yes, formation of this alcohol on this bonds sp2 hybridized carbon with this oxygen is not possible. So this method will not work. You may get this type of questions. So give the starting materials for the preparation of this anisole. Yes, I can write whatever may be the starting material here. I can put bromine also here. I can put bromine here, right? So you may get doubt now. If it is the starting material this and this, what is the product? This is how you will get the question. However, it is the usual way is phenols will not break this bond because this oxygen bond is going to be double bond like character. Yes, I have explained in phenols chapter. So this is why. That is why use phenol as starting material and whatever the other ether you want to make, use this side. For example, if I want to make this benzyloxybenzene CH2, I can write phenyl here. So can you suggest the starting materials here? Yes, students. So the starting materials are phenol plus this side CH2 bromide, benzyl bromide. I can use. Yes, students, let us see the physical properties of ethers. So what are the physical properties usually we come across? It is boiling point or melting point. However, the common ethers we come across are liquids. So stick on to boiling point. These boiling points are increases as the molecular weight increases. At the same time, boiling points decreases as the branching increases. Right? This is a common trend where branching decreases the boiling point. These boiling points are nearly comparable or same to hydrocarbons. For example, the molecular weight, if I take the pentane and diethyl ether, N-butanol. Alkane and diethyl ether boiling points are very near to each other. Its boiling point is nearly 36 degrees centigrade. For example, if I want to show this temperature in Kelvin scale, it will be like this. 309 K. And you know, degree centigrades, it is very easy to remember. 0 degrees ice temperature, 100 degrees centigrades boiling temperature of water, like this. So that you will come to know what is the range of temperature. That is why I am teaching in degrees centigrades. However, in textbooks you will find in Kelvin. Don't confuse. So I am sticking to centigrade scale. And diethyl ether is 32 degrees centigrade. So when it comes to N-butanol, its temperature is about 113. Why alcohols are going to be very high boiling point? Because presence of hydrogen bonding. Solubility of ether, let me stick on to diethyl ether in water. It is soluble about 7.5%. Means if I take 100 grams of ether and dissolve in 100 ml of water, it is going to dissolve only 7.5 grams and remaining is insoluble, right? Whereas this N-butanol, same about 8.5 grams, it is going to soluble. Generalized method, diethyl ether not soluble in water and it gives layer. Suppose if I take diethyl ether and water in a separating funnel, water is going to be down and the diethyl ether is going to be upper layer. Chemical reactions of ethers. So what are the common reactions it come across is the bond which is present in ethers is R, O and R. One chemical reaction is cleavage of oxygen and carbon bond. De-etherification, or if it is methyl group, if it is phenyl group, then it is known as demethylation of ethers or demethylation reaction. Demethylation takes place under drastic reaction conditions. Concentrated hydroiodic acid or HBr or HCl at high temperature, it is going to give ROH plus R iodide. If I use iodide, and the demethylation or the de-etherification capacity is HI is going to be very high, means it easily cleaves this bond, whereas HBr is better than HCl. However, the usual method is using hydroiodic acid HI. At high temperatures, it is going to cleave the ethers. For example, this is the ether. So when I add HI, what is going to happen? Just guess. And another example, if I take simple CS3 and CH2O CH3. So if I take this methoxyethane as an ether and do the reaction with HI, since it is ether is going to have lone pair of electrons, it is positively charged and this is negatively charged, and it takes a proton to give the intermediate of this CH3 CH2O, and CH3 is here hydrogen has come. So in this case the methyl group is very easy or unhindered. This side CH2 CH3 and this is having positive charge. So what is going to happen? This iodide molecule entering onto this carbon or this carbon, which is very easy to enter this side or this side. So this carbon is hindered, right? So this carbon taking up by this carbon is very tough compared to this. So easily it forms bond with this, right? So this is going to out as methyl iodide, and here it is going to like this plus, and this is OH, and the remaining is CH2 CH3. That means whatever the ether you take, bulkier group is going out as alcohol, smaller alkyl group is going out as iodide. However, if I use excess of HI, even this ethanol takes a proton and it is going to form CH2 CH3 and OH is already there and another iodide. At this stage, this iodide enters into this to give CH3 CH2 iodide. In this example, what I said, bulky group, it is going to break here, but it is not so, because this case it is a primary carbon. but this carbon is tertiary carbon. What is going to happen? No doubt it is going to form this at this stage. O hydrogen is here, methyl group, and this is a positively charged. This is methyl and methyl. Yes. So is tertiary compounds undergoes SN2 or SN1 substitution? SN1. So SN1 substitution takes place. So at this stage, what is going to happen? It will be easy to lose this and to form tertiary carbocation, which is stable carbocation, and the remaining is methanol is this side OH, and this tertiary carbocation may undergo elimination to methyl propene. This is OCH3, and let us take one more example. OCH2, this benzyl methyl ether, and when I add HI here, what is the product? When I add HI and heating, what is the product here? Yes. So guess, is it easy to break this bond? No, this bond breakage is not going to take place. Then what is left over? The methyl group. This is positive and negative. It takes up this and it is going to form oxonium ion, and iodide part will be there, iodine minus and O positive. Now what is going to happen? This comes here and this takes up proton to give phenol, and the leftover other part is going to be iodide. Yes. So this is phenol and iodide comes out. When it comes to this, so is it going to break here, here or here? What is your choice? It is very simple, students. It is positive and negative. Let's just protonate this oxygen to give, this is the intermediate O hydrogen and CH2. In this example it is CH3. Just write it as phenyl group. Yes, it is easy to enter iodide from this side and loses this, and I am going to get phenol, here also phenyl, phenyl CH2 iodide. This is debenzylation. So this is benzyl group. So debenzylation can be done using concentrated HI or HB or HCl under heating reaction conditions to give phenols. Aromatic electrophilic substitution reactions. Anisole, methoxybenzene or methyl ether of phenol. So what is the orientation of this methoxy group? Methoxy group orients the incoming electrophile to ortho or para, directing group. This is ortho position, this is also ortho position, either of these two sides, and this is para position. Right? For example, methoxy, it undergoes resonance to form anion. Carbanion forms at ortho position, and the electrophile is electron deficient compound. It loves electron, so it forms electron dense carbanion at ortho position. Then and it forms resonance structure or carbanion at para position, and another ortho position we are going to have carbanion, and the oxygen is tightly attached to this sp2 carbon and it is oxonium ion. Now it will be back to this methoxy here. So these two are same, isn't it? So these two are resonance structures. So because of these resonance structures, what are the positions it is having? Carbanion at ortho, and this is para, and this is ortho. So it is getting carbanion at ortho and para positions during its resonance structure. So aromatic electrophilic substitution in ethers takes place at ortho and para positions. Let us take one example and see. So the usual electrophilic aromatic substitution is nitration. Let us take nitration. And what is the nitrating mixture? Concentrated sulfuric acid, it should be 2 moles, and the concentrated HNO3. This is nitrating mixture. This nitrating mixture generates NO2, electrophile. Our nitration takes place at 2 positions. What are the 2 positions? This is para plus this is ortho. Do you have any guess which one is going to be more or which is going to be major product among these two? This is para, this is ortho. Para position product is a major product, whereas ortho is minor product. Means the yields, if I get 100 grams of this mixture product, in that it is going to be about 90 grams of para and about 10 grams of this. Why? Because this group is already bulky. To enter this electrophile at this position, it is repels. So the incoming nitro group also is very big group. Entering at ortho position is not going to take place that easily. That is why the para is major. Most of the case in electrophilic substitution reactions of aromatic compounds, para product is going to be major. It is a thumb rule. And what is the mechanism? Yes, in all electrophilic aromatic substitutions, there will be three steps. The first step is generation of electrophile. Second step is formation of carbocation or sigma complex. The third step is removal of hydrogen from the sigma complex. This is sulfuric acid and HNO3. So in this case, sulfuric acid is going to act as acid, HNO3 is going to act as base, or it takes a proton from sulfuric acid to give HSO3 minus plus, this is H positive charge, hydrogen from this sulfuric acid has come, and NO minus. This loses water molecule and gives the electrophile. This is NO2, or I can write NO2 electrophile. This is anisole plus this NO2 is floating. It is there in the reaction mixture. It simply takes up this lone pair electron, and let me write at ortho's position. This is nitro, it's attached here. Hydrogen is here, already one hydrogen. Methoxy undisturbed, and this is double bond, and here carbocation. And this resonance structures, if I go on right, it goes out here, positive charge forms here, positive charge forms here, and then comes here. Here it is going to form, here it is going to form. So the overall, the sigma complex, I can write it as like this. The positive charge is resonating in benzene ring, and this methoxy is there, and hydrogen is there, and electrophile in this NO2. Right? Now the third step is removal of hydrogen. To give, it is going to give, in this case, ortho, OCS3 and nitro. And same way you can write the para product also. Usually bromination requires Lewis acid, bromine plus Lewis acid for the generation of bromine electrophile. For example, to generate electrophile, ferric bromide is usually used for the aromatic bromination, where it forms bromine electrophile, then ferric bromide Br4 minus. So this is a usual pattern, but it is highly activating group. So in this case, ferric bromide is not required. Simply take bromine in acetic acid, and this is going to form para bromo compound and ortho bromo, which is major. In this case, para is major product, whereas this ortho is minor. The same thing is bromine is a big atom or molecule, where this is also very big methoxy group, and entering at ortho position is very hindered. So this major para position is very easy to approach this benzene ring. So that is why it gives major product. So Friedel Crafts reaction. So this aromatic electrophilic substitution can be written as like this also, right? Let us take anisole plus alkyl halide. It can be bromide, chloride or iodide. So under Friedel Crafts alkylation, iodides, or for example if I take methyl iodide, gives better yields compared to methyl bromide compared to methyl chloride. So which one I am going to use? Methyl bromide. Yes, and in presence of anhydrous aluminum chloride, the solvent is carbon disulfide. Yes, its boiling point is around 50 degrees centigrade. Take this carbon disulfide and do the alkylation of anisole. You are going to get the mixture of compounds are this orthomethyl anisole plus paramethyl. And what is the ratio of these two? Yes. So usually all the times it may not be 90-10%, but the usual pattern is para is going to be major. Para and this is ortho. Anisole and react it with this acyl group CS3POCl acetyl chloride in presence of anhydrous aluminum chloride. So acetophenone we are going to get paramethoxy acetophenone and orthomethoxy acetophenone. And what is the ratio? Again write it as this is major and this is minor. So how to separate these two compounds? Dear students, it is very simple. Write down steam distillation separates these compounds. How? So this acetophenone is having oxygen, this is also oxygen, and it is very near to each other, so it is going to have some hydrogen bonding. Orthomethoxyacetophenone is going to low boiling point, and this is para is going to be high boiling point. And the first this low boiling point compound distills out with steam, whereas this high boiling point compound distills out later. And one more thing, why this para is going to be high boiling point? Because of this linear structure, I can say. So in a crystal or in a molecule, if it is a liquid, it is going to be tightly packed. So it is symmetric. I can write like this, right? CS3. So it is straight chain, straight some linear structure. Whereas this is it is different structure, right? So it is not going to tightly packed. It is going to be tightly packed, so high boiling point. C2H5. The IPAC name 2-ethoxy 1,1-dimethyl cyclohexane. If I give this compound, write the name, IPAC name. Yes, students. For example, if I want to make this methoxy nitro compound, shall I use bromine plus methanol or phenol paranitrophenol plus methyl bromide? So which one? This is condition 1, condition 2. Which one is going to form? Say in both the case I can have option to use sodium. So which one is going to give this product? Just guess. And this ether, actually butyl, ethyl, C2H5 is ethyl. When I do demethylation using hydroiodic acid, what is the product? Guess. And this is very simple. You can answer this. Right? Question number 1. This is question number 2. This is question number 3. And the question number 4 is aromatic ring C2. When I use hydroiodic acid under heating reaction conditions, what are the products? Yes, students, if you know the answers, please write in comments box so that I will answer you. Otherwise, I am going to post the answers below of this video link. Yes, students, it is very easy to write because the key factor is when you are writing this nomenclature, in this case, dimethyl is going to be prioritized. Ethoxy 1,1-dimethyl cyclohexane, and moreover, since it is attached to 2 carbons, so that is why it is gem dimethyl group is going to be prioritized. And when it comes to these two, this is nitro, this is oxygen. Oxygen and nitrogen, which is priority group? Oxygen and nitrogen group, which is priority group? Oxygen. So in this case, the numbering started from here, whereas in this case numbering starts from oxygen. So write like this 1, 2. I have given the hint. So write down the IUPAC name. And in this case, when you want to follow Williamson synthesis, what I said, nucleophilic substitution at this carbon is not going to take place. So the best way to follow is this method. Take the phenol and do the methylation. And here, when I do this type of demethylation, what is going to have? It is going to form alkene. Elimination is going to take place. And this is, so would say, you know the answer. Write down answers. Yes? So, dear students, I hope you enjoyed this topic. Please subscribe my channel, Venus Academy, if you are not yet subscribed. And don't forget to click on like button and bell button. Sayonara. All the best. Arigato gozaimasu.